Predictive maintenance was developed in response to a specific problem that preventive maintenance could not solve. Preventive maintenance is effective when components wear out according to a time-based pattern. But what if equipment fails randomly with no predictable relationship between time and failure? In such cases, time-based inspections or overhauls are not enough and may even be pointless. This is where predictive maintenance becomes essential. It is mainly applied to address random failures. During equipment operation, various types of stresses increase over time, often in irregular and unpredictable ways. These stresses act on individual components, gradually weakening them or triggering failures. As shown in the diagrams, resistance to stress may remain stable until a sudden spike in applied stress occurs, and this can lead to a breakdown, even if the component had no prior signs of damage. These increased stresses, whether temporary or continuous, can come from many sources, such as operator errors, design flaws, improper assembly, external damage, or temporary disturbances in the process. Stress may also be caused by changing parameters, including mechanical shock, overload, temperature, pressure, voltage, current, pH, and others. The exact cause and effect will depend on the type of component and its operating environment. What's important here is that a single stress event can lower the component's resistance to stress, not necessarily to a critical failure level, but enough to make the component more vulnerable. Predictive maintenance attempts to detect this early degradation before the component actually fails by monitoring these stress factors over time. Complex systems are particularly prone to random failures, as their numerous components and interconnections increase the number of potential failure points. Additionally, each element within such a system may wear out at a different rate. External factors such as temperature, dust, vibration, and humidity can also contribute to the randomness of failures. All of this reduces the resilience margin of components against degradation, and their interdependencies make it difficult to predict the consequences of a failure. Systems that are prone to such failures include electrical, hydraulic, pneumatic, and mechanical systems. Although temporary load spikes may not immediately cause visible damage, they permanently reduce the resistance of system components to future stress. As a result, each subsequent load peak can become a critical point, and the moment it occurs is difficult to predict. In practice, this type of failure may happen days, months, or even years after the initial event. Let's consider an example. Imagine the winding of an electric motor. If the motor experiences a series of random overloads, each of those overloads may cause subtle but hard-to-detect degradation of the winding insulation. You don't know how much degradation has occurred, and you don't know when the next overload will happen. Eventually, the insulation may break down, but there is no predictable pattern. This randomness makes it nearly impossible to define an effective time-based maintenance schedule. And this is why traditional approaches based on regular inspections or replacing components at a specific age are not effective for this type of failure. It is often said that using preventive maintenance for random failures is like throwing darts at a target while blindfolded. You might get lucky and replace the component just before it would have failed. But in most cases, you will either replace it far too early or too late, after damage has already occurred. In this context, predictive maintenance is the only strategy that provides a rational way to deal with such failures. Let's take an example from industry. For many years, a common practice was to replace bearings in machines after a specified number of operating hours, based on the assumption that bearing failures increase with age. However, bearing life is statistical in nature. It's random and probabilistic. Even though bearings are made of high-quality steel, they can still fail randomly due to microscopic inclusions or contaminants in stressed zones, variations in operating conditions such as speed, load, or environment, or non-uniform wear of components. Because of this randomness, manufacturers do not provide a single value for bearing life. Instead, they use a statistical model known as B10 life. This refers to the number of operating hours after which 10% of bearings in a statistical group are expected to fail, while 90% should still be operational. But here's the challenge. It's impossible to know which specific bearings will fail first. This variability is clearly illustrated by the failure distribution chart shown on the right. It comes from a study involving 30 identical deep groove ball bearings, Type 6309, installed on identical machines and operated until failure. On the x-axis, you can see the bearing number, from 1 to 30. On the y-axis, the number of revolutions until failure. The graph shows a wide spread of results. Some bearings failed early while others lasted much longer, despite being identical and operating under the same conditions. This graph shows that every bearing will eventually fail. However, the wide variation in bearing life clearly rules out the possibility of any effective time-based maintenance strategy. This material is an excerpt from the course Maintenance Mastery. Want to learn more? Visit rcm2.org.